Welcome to Calculus. I'm Professor Greist, and we're about to begin Lecture 35 on Arclength.
After ascending to the heights of infinite dimensional spaces, we're going to come back down to Earth and consider simple one-dimensional curves. As we now know, one-dimensional volume is really just length, and we'll begin this lesson by considering the length element.
We begin our discussion of Arclength with that formula that you know is coming, namely that the Arclength is the integral of the Arclength element. The question is, how do you determine the Arclength element? Well, we think of it, of course, as a very small, infinitesimal piece of the curve. Let's say that we knew the graph in the plane and we set up a right triangle with base dx and height dy. Then what would the length of this hypotenuse be? Well, from Pythagoras, it would be the square root of dx squared plus dy squared. Well, that's simple enough, but how do we make that work in practice? Well, in the one case where we have an implicit curve, that is, for example, some curve where y is defined as a function of x, and we're looking at the graph. Then, when we write out this formula, what do we have? Well, from the chain rule, we can express dy as dy dx times dx. When we square that and follow through with the algebra, we can factor out a dx squared from under that square root sign. Of course, the square root of dx squared is dx, and we're left with dl is the square root of 1 plus dy dx squared times dx. That simple manipulation of differentials actually works. For another example, maybe we don't have a curve that's expressed in terms of a graph. Maybe we have a parametric curve where the x and y coordinates are given by some function of t. Such curves can swoop around and cross themselves in interesting ways. In this case, applying the same differential analysis, what do we have? Well, if x and y are given as functions of t, then dx is dx dt times dt, dy is dy dt times dt. Once again, we see that there's a dt squared under that square root that can be factored and pulled out, and we obtain an Arclength element that is the square root of dx dt squared plus dy dt squared times dt. Let's see this put to work in an example. Compute the length of a simple circle of radius r in the plane. We'll do this parametrically, writing x as r times cosine of t and y as r times sine of t. We have to be careful to say what the bounds on t are. T is going from 0 to 2 pi, let's say. Then, in this case, the Arclength element is square root of dx dt squared plus dy dt squared times dt. When we differentiate cosine and sine, we get, very simply, r squared sine squared t plus r squared cosine squared t dt. We see that it's easy to factor out an r squared, and applying the simplification sine squared plus cosine squared equals 1, we have an Arclength element that is r dt. And to compute the length, we integrate r dt as t goes from 0 to 2 pi. And that gives us simply 2 pi r, the answer that we all know. For an example involving an implicit curve or a graph, consider the equation y equals log of sine of x, as x goes from pi over 4 to pi over 2. I don't know what the graph of that looks like, but I don't need to, since I know the formula for the Arclength element. It is square root of 1 plus dy dx squared times dx. Now, when I compute the derivative of log of sine of x, what do I need to do? Well, from the chain rule, that's 1 over sine of x times the derivative of sine, namely cosine. We can simplify that a little bit. 1 plus cotangent squared x is, of course, a cosecant squared of x. Taking the square root gives an arclength element of cosecant x times dx. And now, to compute the length, we need simply to integrate cosecant x dx as x goes from pi over 4 to pi over 2. I may or may not be able to remember the integral of cosecant, but I can assure you that it is minus log of absolute value cosecant x plus cotangent x. When we substitute in those limits, pi over 4 to pi over 2, then we get minus log of, cosecant of pi over 2, that's 1, and then plus is a 0 there, and some other terms. I don't know. That's too much to do in my head, but I think that the final answer is log of quantity 1 plus square root of 2. One of the sad truths about arc length problems is that so often the integrals get messy because of that square root, and they can be pretty difficult to evaluate. But it's not all bad news. There are some very interesting problems that we can solve with integrals. One is the catenary. That is the shape of a hanging cable. Here's a fact that comes from physics. The rate of change of the slope of such a hanging cable is proportional to its length element. Now, what does that mean? If we set up some x and y coordinates to describe the curve, then what this statement claims is that the slope of the cable, which we can interpret as dy dx, changes, that is, has derivative that is proportional to the length element. That means we could write it as kappa times dl, where kappa is some constant. Now, how do we make sense of this differential equation and then solve it? It's got two derivatives. But if we let u be equal to dy dx, then we could write this as du dx equals kappa times the length element, in this case, square root of 1 plus u squared. That is a differential equation that I think we're going to be able to solve. Indeed, this is clearly a separable differential equation. And so, moving root 1 plus u squared on the left, we have on the right kappa dx. Integrating both sides yields what? Well, on the left, we're going to have to apply a substitution. And I think this is an ideal candidate for a trigonometric substitution. If we let u be sinh t, then du is cos t dt. And we have on the left the integral of cos t dt over square root of 1 plus sinh squared t. The right integrates simply to kappa x plus a constant. On the left, we have some great cancellation. 1 plus sinh squared is cos squared. The square root removes the square. The cos's cancel, and we're left with the integral of dt, namely t. If we substitute back in for u, we see that this is really arc sinh of u equal to kappa x plus a constant. If we take the sinh of both sides, then we obtain u as sinh of quantity kappa x plus c. If we set up our coordinates so that x equals 0, right at the minimal point of the curve at the bottom, then since sinh of 0 equals 0, we can say that that constant of integration vanishes, and the slope at x equals 0 that is u, vanishes also. Therefore, we have u equals sinh of kappa x. Now, this is not exactly what we were trying to find, since recall, u is the derivative dy dx. How do we get y for the shape of the curve? Well, we integrate. The integral of sinh is cosh. We have to pull out a factor of kappa, and so we get y is 1 over kappa cosh kappa x plus some constant of integration. Why not? That would be how high off the ground the bottom hangs. All this tells us the wonderful fact that the catenary hangs as a hyperbolic cosine. That is the shape of a hanging cable or chain. With this shape decided, let's compute the length. It is, of course, the integral of the length element, and in this case, integrating the square root of 1 plus dy dx squared dx is going to work for us. Let's set the limits to be x goes from negative L to L, where L is half of the projected length to the x-axis. Then, in this case, we need to substitute in for dy dx, but that is sinh of kappa x, leading to an integral of the square root of 1 plus sinh squared of kappa x. We can substitute in cosh squared for 1 plus sinh squared. The square root goes away, and we're left with the integral of cosh kappa x dx. That is, of course, sinh of kappa x divided by kappa. Evaluating from negative L to L gives us 2 over kappa times the hyperbolic sine of kappa times L. Now, what does that mean? Well, one of the things that implies is that we have exponential growth in this length of the chain, given linear growth in L, the width. That's a bit of a surprising result, but it falls out easily from what we've done. Let's take a look at an example involving a spiral. We're going to use a parametric representation, like we did for the circle, but with a 1 over t coefficient out in front that causes you to spiral in as t increases. We'll let t begin at 2 pi so that we start to the right. The length element in this parametric case is the square root of dx dt squared plus dy dt squared dt. Now, this is going to involve a fair bit of differentiation using the quotient rule and what we know about sines and cosines. I'm going to leave most of the simplification work to you here, but do note that when you multiply these terms out, there's quite a bit of cancellation between the cross terms, and using the fact that sine squared plus cosine squared equals 1. In the end, you get the square root of t squared plus 1 all over t squared dt. Now, integrating that is not going to be so bad, maybe. Let's try. What we need to do is integrate as t goes from 2 pi to infinity. Now, I don't see a really good substitution at this point, but what I can do is say that the t squared is the dominant term under that square root. And pulling that out and simplifying, we get 1 over t plus something that's in big O of 1 over t squared. Now, I know that that leading order term leads to a divergent integral. When you integrate 1 over t from a constant to infinity, that diverges. We could follow the steps as we've done back in lecture 27. But what this implies is that we have an infinite spiral. That's a little bit of a surprise. There's an infinite amount of length in that simple-looking spiral. There are more surprises still. Let's say that you looked at a spiral that was not smooth, but rather based on squares descending. Let's say at each step you're multiplying the length of the last segment by some factor, r. Well, what would you do in this case? In this case, integration becomes simply summation, and you would add up the lengths of all these segments. We recognize in this our old friend, the geometric series. And so, in this multiplicative case, it's possible to have a finite length spiral. Now, other stranger things could happen. Let's say we took a line segment and removed the middle third and replaced it with 2 line segments, each with length 1/3. Then we would have a new curve whose length is 4/3. Now, if we took each of those resulting segments, removed the middle third, and replaced with 2 smaller segments as shown, then we would be multiplying the length of the entire curve, again, by a factor of 4/3. Now, I think you can guess what we're going to do. We're going to continue this process inductively, at each stage multiplying by a factor of 4/3. In the end, we obtain an interesting object called a fractal curve whose length is infinite, even though the curve is of bounded extent. This is the kind of interesting thing that can happen when you start using your imagination.
And so we see that even some simple one-dimensional curves can pack some surprises. Be sure to internalize the idea and computation of a length element. We're going to need it in our next lesson, where we compute surface area.